Okay, so today's lesson is on Archimedes' principle, but before we get into Archimedes' principle, we have to talk a little bit about buoyancy. So what is buoyancy? Buoyancy is an upward force on an object that's due to a difference in pressure on that object when it's submerged in a fluid. So if we have this fluid right here, so we have some fluid right here, and we have some original height, some depth below, I'll call that y1, and some other depth below, we have that as y2. There's some p1 going this way, and there's some p2 going in that direction, the upward direction. So now the basis of this is that p2 is got to be greater than p1 because p2, the surface that is exposed to P2 is deeper, so there's a greater depth, so therefore there's a greater pressure. So what we can say is that the difference in pressure is P2 minus P1, and since P is equal to rho g h, where h is the depth, I have rho times g times y2 minus rho times g times y1. So we could pull out that rho, and we have some y2 minus y1. Or, excuse me, we pull out both the rho and the g. Now, it's important to realize that that rho is the density of the fluid, right? So that density is due to, the pressure is due to the fluid, the column of fluid that's above that surface. So based on the definition, since pressure equals force over area, if I want to figure out a buoyant force, it's got to be nothing more than the change in pressure times the area. Basically, you're multiplying, cross-multiplying here the P and the A. And so since delta P is the density of the fluid times G times Y2 minus Y1, which in this case we're going to call H, so H is the height of the container. So we end up getting rho of the fluid times G times H. Okay, and so then that becomes that buoyant force is rho of the fluid times G times H times that area. Okay, so this first part is your delta P. But what's interesting is this H times A. That H is that height of that cylinder, and then the A is the area on the top and bottom, which happens to also be the volume. Okay, so the buoyant force is equal to the rho of the fluid times G times the volume of the object. Okay, and that's the equation that you'll see in your reference tables. So, which leads us to Archimedes' principle. And Archimedes' principle says that the buoyant force on a body submerged in a fluid is equal to the weight of the fluid displaced. Now, that has some important consequence to it, because what that's saying is that the F of B is equal to the F of G of the displaced fluid. So this is the displaced fluid, not all of the fluid. So if you know how much fluid is displaced, the weight of the fluid displaced, then you can also tell the buoyant force. Okay. All right, so let's look at two examples here, and then we will work out the other one, part C, in class. So it says a 4-kilogram body is submerged in H2O and doesn't sink or rise to the top. So that means that its velocity is 0, and which means that the sum of the forces must also be equal to 0. So I have a downward force of gravity, but I also have an upward buoyant force due to the difference in pressure. And if it's not rising or sinking, those two are equal. So I'm going to start off with that statement, F of B is equal to F sub G. And the buoyant force is the density of the fluid times g times the volume of the object. And the force of gravity is the mass of the object times the gravitational field strength. So right off the bat, I see g's cancel out on both sides. So now I have the density of the fluid times the volume of the object equals the mass of the object. Remember this substitution that we can write rho v in for the mass of the object. So this will be the density of the object times the volume of the object, and g is already canceled out. And so we could see that v of the object also cancels out. So the density of the fluid has got to be equal to the density of the object. That's what it's asking. What about the 4 kilogram body that sinks? Well, once again, the v is 0, so the sum of the forces must be also equal to 0. Well, we have a downward force of gravity, and we have 2 upward forces. There's a buoyant force, there's some F sub b, but it's also touching the surface, so there's got to be an upward normal force as well. And I don't know how these two compare to each other, but I know they go in the same direction. And I also know that the forces down must equal the forces up. And I know the force of gravity is the density times the volume of the object times g, so this is mg, which is equal to the normal force plus the density of the fluid times the g times the volume of the object. So here's what's important. We have the volume of the object on that side and times g, and the volume of the object times g on the other side. But on this side of the equation, we have this normal force. So we're adding something to that quantity. And since the 2 parts of that quantity are the same as the 2 parts over here, if I'm adding something to that term, the term on the right here, then this density, the density of the object, is got to be greater than the density of the fluid, which you guys already know. If it sinks, then we can conclude that. But here's why we can conclude that. So if we want to know how does the mass of the object compare to the mass of the water displaced, well, that's where we have to apply Archimedes' principle. So we have the density of the fluid is equal to the density of the object, okay, for the first case. And so density, since density equals m over v, then this is the mass of the fluid displaced divided by the volume of the fluid displaced, which is equal to the mass of the object divided by the volume of the object. So since the weight of the fluid displaced has got to be equal to the buoyant force, we can also conclude that the fluid displaced, the volume of the fluid displaced, is got to be equal to the volume of the object itself, if it's fully submerged. And that's an important if. So in this case, the mass of the fluid is equal to the mass of the object. And that is the mass of the fluid displaced, once again. And then likewise, we can make the same argument that the mass of the object here is got to be equal, greater than the mass of the fluid displaced, since it is sinking. All right, so that's all for now. We'll finish up the rest of these tomorrow. I hope you have a good night. Thank you for watching. Bye-bye.